Hi guys, this is Rahul Chaturvedi and you are watching Telecom Notes. Guys, please subscribe this channel and stay connected as we are having the upcoming videos on the multiple topics also. So today we are discussing about Scfdma, single carrier frequency division multiple access. So let's start. So before going to Scfdma, first have a look over OFDM transmitter. So it will be helpful to know why Scfdma and what is the benefit of using Scfdma in uplink. So going to the OFDM transmitter first. Starting from the block diagram of the transmitter, as you can see, the higher layer protocol bits is received from the higher layer. Then after that particular bits are transmitted into the symbols, and the phase shift of that particular symbol has been just provided. It's been just provided in such a manner that they are just orthogonal to each other. So each symbol is orthogonal to each other. That's the orthogonality concept of OFDMA. After that particular number of symbols are just put it in parallel, because right now they are in a series. So after putting in parallel, you will have a look. As you can see over here, you can see there are multiple. Let me just take a marker. Right now, as you can have a look, that each of them is having 15 kilohertz spacing. That 15 kilohertz is one single carrier frequency, and on which these particular are having that weightage, that particular frequency. And this is the phase, 315 degree, 45 degree, 225 degree. So these are the phase shifts through which they are orthogonal to each other, and these are the waves. As starting from 0, it's 15 kilohertz, and 15 to 30, that means that this one is 30 kilohertz, this one is having 45 kilohertz. Just like is the positive side, and at the bottom you will find this as a negative side also, that minus 15, minus 30, minus 45, and so on. After that, you can have a look that it's RE mapping, resource element mapping, and it's having the subcarrier spacing of 15 kilohertz per each, as I have told you right now. So here you can have a look that this one is the frequency and this one is the time, in which I have just put it, taken as an example over here. It's 110011, and I have just put it here. It's 1100 and 11 in 45 kilohertz, 30 kilohertz, and 15 kilohertz. So as you can see, at a particular amount of time, you can see different frequencies over here. So that's what I have just written here, that symbols placed as per the frequency domain F1, F2, F3, and Fn, so on. Now after that, you can see we have done the inverse FFT. After putting the inverse FFT, that from the frequency domain they have just changed into the time domain again, and after that we have just gone through the digital to analog converter, and after digital to analog converter we have put it the RF carrier also on that. After putting the RF carrier, that means that particular carrier frequency, we have put it the phase shift again component, and after that we transmit through the antenna. So there is the OFDM transmitter, in which we are putting the IFFT only. Now looking at the blocks diagram again, as you can see, E node B transmitter bits for UE1, UE2, and UE3. You can have a look over bits changing into the symbols here, and after that we have just changed from series to parallel. Now this is the RE mapping. As I have just told you, this one is the RE mapping. We have put it earlier. Just in the same manner I have just created right now. This is the time and this one is the frequency. And after that we have just done the IFFT, inverse Fourier transform, and we have changed to parallel to series. After putting that parallel to series, we have put this cyclic prefix also, and analog transmitter, and I have, after that you will just transmit it. The vice versa procedure is at the end of the receiver, that you will find analog receiver, cyclic prefix removal, serial to parallel. Here you will find this yeah here you will find that we have just used the FFT so that it can be just converted from the time domain to the frequency domain again, and phase removal, that's the phase shift we have just provided to each and every symbol, and after that parallel to series, and that symbols are converted back into the bits, and that particular bits are received over here. Moving on to the next slide, is OFDMA working? Data placed in OFDMA is having the use of different frequencies at a particular instant of time, as I have just told you earlier. So suppose we are using the subcarriers having the data distributed on n frequencies, so the power needed in the n different frequencies is also n watts. The main reason why we are using the Scfdma is this peak to average power ratio. In the OFDMA case, we are having the peak to average power ratio as n, while in Scfdma, I'll just tell you in the further slides what's the difference and how we'll just coming as a solution with the Scfdma. So the n watt power is easily used by E node B as it has large unit of power battery stored to transmit. That's why we use the OFDMA transmitter in downlink from the E node B side. Why we need the Scfdma in UL? As we know, we use the mobile phones having the limited amount of battery, so we cannot afford n watt power at our end. So how Scfdma works? So you guys, we can just pause for 15 seconds and you can have your guesses that why we are just using Scfdma. Okay, move on to the further slide. Data placed in the Scfdma is having a use of single frequency. So in this one we are using the single frequency. All frequencies are combined by using the FFT before going to the IFFT of each subcarrier. So in the previous transmitter you have just have a look that we only use the IFFT, but in the case of Scfdma we have used the FFT also. So as you can see here, right now the frequency remains same because it's been just combined by using the FFT, and the time domains are different now. So as you can see, the mapping right now is 110011 is not in parallel, is in a series form right now. So in this we are using the data distributed on single frequency, so the power needed in a single frequency is also single watt. Example, 1 watt per frequency per time t1. As we have done n fractions of blocks in the time domain, the peak to average power ratio in Scfdma is 1. So that's the only reason we are using Scfdma in uplink. So now coming to the Scfdma transmitter. let me take the highlighter first, laser point. Yeah, so as you can see, the higher layer protocol bits, again the same 110011, and we have just converted bits into symbols. After that, we have just provided the phase shift like the same in the OFDM transmitter. After that, it says we just put it in the series to parallel format, and after that we have just added in the Scfdma is the FFT. After doing the FFT, that particular number of symbols have been just combined up and creates a single carrier, and after that it has been just mapped like you can see on the top that it's having T1, T2, T3 time, and in place of parallel they have just put it in a serial way, and the frequency remains same in using for the number of sections in the time domain. Earlier we are having the segmentation in the frequency domain, while the time domain remains same for putting the symbols. After that, it has been just converted back from digital to analog, and it has been just put it over the RF carrier, which conveys that particular data. After that, we have just put it the phase shift, and it has been just transmitted from the antenna. Now coming to the detailing of the Scfdma transmitter and receiver, as you can see the bits right now, you can have a look. It's been just bits to symbols, converted into bits to symbols. After that, serial to parallel converter. As you can see, it's forward FFT also, while in case of OFDMA it's not present. Then resource element mapping. After that, the same in case of the OFDM also, we are having IFFT, parallel to serial converter, cyclic prefix insertion, analog transmission, and that particular data has been just transmitted. And at the receiver end, it's having analog receiver having the cyclic prefix removal, serial to parallel, forward FFT for cancelling the effect of inverse FFT. And after that, we are having resource element selection to just extract out what are the exact particular data we have to just taken out for having the actual data. Then the phase has been just removed as we have just provided the phase shift earlier. Then inverse FFT to cancel the effect of forward FFT, and then series to parallel in case of transmitter, as you can have a look. The same way we are having parallel to series to just convert that particular number of bits in a series format, and after it has been just forwarded to symbols to bits, that converts that particular number of symbols to bits, and that bits are received at the receiving end. Now coming to the LTE identifiers, we are having the number of IDs having their meaning, that's the full form, and in description they have just provided that why they are provided to the LTE, and what are the actual reason that how they work. After that, we are having the structure, that how it has been just created by the number of combinations of other codes. So coming to the IMSI, International Mobile Subscriber Identity, it's having unique identification of mobile LTE subscriber network. Okay, gets the PLMN of the subscriber. IMSI is the PLMN, and ID plus MSIN is the combination of MCC, that is the country code, MNC, that's the network code, and MSIN. Coming to the PLMN ID now. PLMN ID is Public Land Mobile Network Identifier, having the unique identification of PLMN, and the PLMN ID is the combination of MCC and MNC. Coming to MCC, the mobile country code. It's having the 3 digits. It's already assigned by ITU. There's the network code now, mobile network code assigned by national authority, having 2 to 3 digits. MSIN is mobile subscriber identification number, assigned by the operator, having 9 to 10 bits. That's your mobile number actually. Coming to GUTI, globally unique temporary UE identity, to identify a UE between the UE and MME on behalf of IMSI for security reason. Having GUTI is actually the combination of GUMI, that is GU MME ID. It's global unique MME ID, and MTIMSI. Coming to STIMSI now first, it's SI temporary mobile subscriber identity, to locate identify a UE in short within a MME group. So STIMSI is the combination of MMEC, that is MME code, and MTIMSI. Coming to MTIMSI now, MTIMSI is MME mobile subscriber identity, that is unique within the MME, having 32 bits. So coming to further slide, and you can have a look. It's GUMI right now, GUMMEI, that is global unique MME identity. To identify MME uniquely in global, GUTI contains GUMI. So GUMME ID is actually the combination of PLMN ID with MME ID. What is MME identifier now? So for MME identifier, we are having MME group identifier plus MME code. So it's the combination of MME GI and MME C. Coming to MME GI, that is the group identifier, having the 16 bits. And when it comes to code, we are having the MME code, and it's having the 8 bits now. And the description is to identify MME uniquely within the MME group. Coming to TAI, that is tracking area identity, to identify a tracking area. TAI is the combination of PLMN ID, TAC, P gateway, and tracking area code is actually of 16 bits, and is to indicate eNode B to which tracking area the eNode B belongs. Coming to the tracking area identity list, that is TAI list, you can move into the cells include the TAI list without any further update. So it's having the variable length, having the number of TAI in the list. Now coming to the particular GUTI, because that's the most important part. So I've made the combination for the GUTI, how GUTI have been just created. It's MME code of 8 bits and MTIMSI of 32 bits, that is unique within the MME. With the combination of these two, we have get the STIMSI of 40 bits, while having the combination of PLMN ID, MME GI, and STIMSI, we'll get the GUTI. So the GUTI is typically of 80 bits, in which PLMN identity is having 24 bits, MME group ID is having 18 bits, and the STIMSI is having 40 bits. So that's it from my side. Thanks for watching the video. Let me know if you are having any query or suggestions. Thank you.